In our third installment in this study of circular motion, we're going to look at centripetal force. So one of the things that attracts people to physics is the level of certainty that it offers. Things in physics tend to go through a tough process of rigor to show that they're correct, but once they are shown to be correct, they will stick around, they'll stand the test of time. And one of the reasons for this is the reliance on maths and mathematical proof. So physics is associated with numbers, and numbers don't lie. One famous physicist, Ernest Rutherford, once said, if your experiment relies on statistics, you ought to have designed a better experiment. So in physics, we don't like to make these general observations. It's better when things are shown with a lot more certainty. So as we begin this section, we're going to take a look back at Newton's second law of motion. So Newton's second law of motion states that when an unbalanced force acts on a body, the rate of change of the body's momentum is directly proportional to the force and takes place in the direction of the force. So that's often summarized down into the formula F equals ma, which is a special case of the Newton's second law, and we've shown that experiment in the lab. So we're starting off from here. We've shown that F equals ma. We've said previously that in circular motion, a body is said to be accelerating. And if it is accelerating, therefore it must have a force because it has a mass, and now we're saying that it has an acceleration. So if it has a mass and acceleration, then it must have a force. So we can't gloss over this fact, and we need to address this problem. So as the body is traveling at constant speed, the force cannot be in the direction of motion. And what that means, the force being in the direction of motion, means it's not speeding it up or slowing it down. If it was in the direction of motion, either behind it, so to speak, or against it, then the velocity would not be constant. So we can rule out that it is in front or behind. This force that it experiences, the force given by this equation, is called the centripetal force, and it always acts towards the center of the circle. So it's a force between the object and the center. So that is the way that the thing is acting. So that's the centripetal force. It results from F equals ma, and it always acts towards the center of the circle. So we take a look at the definition. The definition, centripetal force. So if a body is moving in a circle, the force towards the center needed to keep it moving in that circle is called the centripetal force. So if you did not have this force, you could not keep moving in a circle. So it's an essential part of circular motion. Since centripetal force acts towards the center of the circle, the acceleration is towards the center. So this acceleration is called the centripetal acceleration. So the centripetal force leads to the centripetal acceleration, and it's always towards the center because that's the same way the force travels. Moving on then to look at centripetal acceleration. So the definition, if a body is moving in a circle, the acceleration it has towards the center of the circle is called the centripetal acceleration. So again, that's a definition we need to know. Centripetal force is an umbrella term for all forces that could hold an object, so any force that would keep the object in this circle. So I like the phrase umbrella term, so it's a catch-all term, so it will account for many different forces. Centripetal force isn't something you experience in nature. The ones you would experience in nature will be tension. So if you're swinging something on a string, the tighter the string is, the more force that it would show. Often it could be gravity. So for example, gravity could hold the planets in their orbits. The force that keep it moving in the circle could be friction. So they're the real forces that fall under this umbrella term of centripetal force. So we take a look now to get into the maths of this. So the factors on which centripetal force depends. So what will give you a large centripetal force or a small centripetal force? So how difficult it is to keep an object in circular motion depends on a number of factors. So you want to keep something moving around. So the first one is the mass. If you have a bigger mass, you're going to need more force to keep it moving in a circle. So force is proportional to mass. The radius is also important. The longer, say, the rope you have, the easier it is to swing something around. If you have a very heavy mass on a very short string, you're not going to be able to swing that around. If you have a longer rope, then you might have a chance of doing that. So the force is proportional to 1 over radius. As radius gets bigger, you're going to need less force. And finally, the velocity. If you want to keep something moving around very quickly, you're going to need more force to keep it in that circle. And again, you think if you have a weight on a string, the faster you spin it, the more likely the string is to break. So the tension increases, and then it goes beyond the tension that the string can handle. So we tie these things together. We have M and V. They're multiplied. So M goes up, F goes up, V goes up, F goes up. And we have R as an inverse proportion, so that goes on the bottom. We don't need to show this by experiment, but the thing is proportional to not just velocity but velocity squared. So we take two formulas here for centripetal force. So the first one is F is equal to mv squared over r. So again, that comes from this relationship, and we can adjust that to F is equal to m omega squared r, where omega is the angular velocity. So we're going to take a look then at how this comes, and again, like I said, physics relies on maths, so we can show from our basic first principles, our F equals ma law, how we get these two. So I've worked with this one on the left and this one on the right. So as F equals ma, which we've accepted as a law in science, one of Newton's laws, acceleration is equal to F over m. From the above, we can substitute F out, so F becomes mv squared over r. So we sub those in like this, so acceleration is equal to mv squared over r, and we have the m here from the Newton's law formula. So this m on the top line cancels with that m on the bottom line, and the acceleration, then we get a formula for acceleration, which is v squared over r. So that's another formula, and again, it's a formula heavy chapter, so our acceleration is equal to v squared over r. Sometimes this information might be more readily available, so this will be an easier one to use. Again, we start off from F equals ma, and a is equal to F over m. We have this relationship for force, so force is m omega squared r, so we sub out the F and put in this m omega squared r, and again, that is over the mass of the object coming from here. So the mass from the force formula cancels with the mass down here, so we get a is equal to r omega squared. Typically you put a squared term last, like you had a 4x squared, so a is equal to r omega squared. So there are our formula for this section, and the next thing we need to look at is questions to get some practice with these. It is getting a bit more difficult now because we have a lot of different formulas appearing, but it's just a matter of using your tables, getting the formula down, seeing what information you have, and then choosing the most appropriate formula. So that is our study of centripetal force and centripetal acceleration. Sometimes called centripetal force and centripetal acceleration, just depends on where you put your emphasis. So don't be confused by the different terms. So centripetal or centripetal acceleration and centripetal or centripetal force.